I use radio telescopes like the Very Large Array located in New Mexico to collect data. I'm interested in studying galaxies and galaxy evolution, and I'm particularly interested in magnetic fields in galaxies, which is something a lot of astronomers try to stay away from because they're complicated and messy to deal with. But luckily, when we've got telescopes like the Very Large Array, we're starting to get a lot more data that is helping us understand magnetic fields. So here is an example of magnetic fields in a spiral galaxy, as you can see with those little orange segments, those bars. I am also a dog mom, a baby mom, and a Frisbee player. So those are other things that occupy a lot of my time outside of teaching and research. So happy to talk about those things offline as well if anyone's interested. So to get started, I would like to convince you how we can be time travelers as astronomers. So here is an example of an image with the Milky Way up in the sky behind an optical telescope up on Kitt Peak. So I think that we are all time travelers every single time we look beyond the Earth because it takes time to travel. And it turns out that there is a cosmic speed limit that nothing can travel faster than, and that is the speed of light, or c, like astronomers and physicists like to use to designate important quantities. So the speed of light is 300 kilometers per second, or 607 million miles per hour, okay? So it's really fast, but it's a limit, right? So that means that if you're a photon traveling through space, it's gonna take you time to get someplace, right? Going back to our basic physics, right? In elementary school or middle school, right? Speed is equal to some distance traveled divided by the time that it takes to go that distance. We can manipulate that equation to get time is equal to distance divided by speed. So if something is some distance away from us and it travels at some speed, there's gonna be some time delay between when that photon is emitted and when we can observe it. So, for example, if we're lucky enough to have a clear sky tomorrow night and we look to the southwest at sunset, we'll see a beautiful conjunction or near conjunction of Venus and Saturn on the sky as they're following the newly waxing moon as it is setting closely behind the sun. So when you look up at those objects, the average distance to the moon is 238,900 miles. I say average because its orbit isn't exactly circular, so it's not always the same distance from us. And it will take light 1.3 seconds after it has reflected off of the surface of the moon to reach us here on Earth. And so we say that the moon is 1.3 light seconds away. The sun is 91 million miles away, and so it takes light 8 minutes to get to us, or we say that the sun is 8 light minutes away. So the sun could have disappeared 8 minutes ago, or 2 minutes ago, and we won't know for another 6 minutes, right? Because the light takes that amount of time to get to us. Venus, on the other hand, is currently at a distance of 142 million miles, because it orbits the sun and we orbit the sun, so that distance is always changing. But that means that right now, the sun's light reflected off of Venus is gonna take almost 13 minutes to get to us, so 13 light minutes away. And the last object that we, if we're lucky, would be able to see tomorrow night, Saturn, is 994 million miles away. So it's going to take over an hour, almost an hour and a half, for that light to get to us. All right, so just in this small scale, right, we can look back in time an hour and 30 minutes ago every single time that we look at the Saturn from Earth. So if we go back to that image that I had on my title slide, this is the Carina Nebula. It's located 7,600 light years away from us, all right? So it's gonna take almost 8,000 years for light emitted in this star-forming region to get to us. If you're curious about where this is located, you're gonna have to go to the southern hemisphere to try to observe it, or well, to actually observe it. You can't observe it from the northern hemisphere from here. And if you're familiar with constellations in the southern hemisphere and you find the the very popular, very bright on the sky Southern Cross, the Carina Nebula is actually visible with binoculars. So if you're lucky enough to be in the southern hemisphere and can get your hand on some binoculars, it's a pretty amazing thing to check out. All right, but this is an image taken with a telescope here on Earth. If we send up a satellite with a telescope on it, like the JWST, we're able to get much more interesting images because we don't have to deal with the Earth's atmosphere. So it turns out that we are very, very lucky here on Earth to have the atmosphere that we have. We can breathe. If we didn't have the atmosphere, astronomers would be able to do a lot of more interesting science for a lot cheaper because we wouldn't have to build space telescopes, right? To send telescopes above the Earth's atmosphere. But we're all living here on Earth, so it's a good thing that we've got that atmosphere. But when we send a satellite like the James Webb Telescope up into space, we can get some really magnificent images. So I'd like to introduce this telescope, the James Webb Space Telescope. Very briefly here, I'll go into a bit more detail shortly. But the James Webb Telescope is an infrared space telescope. So that means that the light that it collects is in the infrared portion of the electromagnetic spectrum. So it's not the light that we can observe with our own eyes. So we're going to be seeing a different part of the electromagnetic spectrum whenever we look at images from the James Webb Space Telescope. We consider this to be the successor to the Hubble Space Telescope because it is building off a lot of the phenomenal research that was done with the HST. It is located at the second Sun-Earth Lagrangian point, or L2. I will have a picture of that in a second. And just briefly, why do we want to have an instrument like the JWST? Well, because space. It's interesting. There's a lot of things out there that we don't understand. So we need these types of instruments to really start to unlock a lot of the mysteries in the universe. So interesting things in space that we will be able to look at with JWST are star formation, exoplanets, galaxy formation, and a whole lot more. So what is the JWST? Well, this is a diagram of the telescope. It has a bunch of different interesting features on it that I'd like to point out. Some of the, the things that if you see an image of it that, hopefully you'll be like, oh yeah, I know what that thing is now. So on the far left, we see the momentum flap. If anyone's familiar with boating or sailboats, it is similar to, now I'm blanking on the name of the part of not the rudder, the flap, something flap. It'll come to me in a couple of slides. But anyways, it's used to prevent the sun's radiation from tipping the telescope. So it helps to balance the telescope against the solar pressure of the radiation coming from the sun. This telescope you could consider it to be a green telescope. It uses solar energy. It's got a solar array to collect those photons and then power its computing systems and everything. It has an Earth-pointing antenna, which is critical for us to be able to communicate with the telescope and for the telescope to send information back to us. The spacecraft bus I think about that as like all of the internal organs of the telescope. It has the computing center, the communication center, the thermal center, so to help regulate the temperature of the telescope. It has the thrusters and the propulsion system are all managed in there. So that's a very important part of the telescope. There's a star tracker that just helps it, approximately point to where it needs to go on the sky. I'll talk a little bit more about how it does the fine pointing in a couple slides. And then one of the most fascinating pieces, I think, of this telescope is the sun shield. It is the size of a tennis court. So to start to get a sense of how big this instrument is. And if you are on the sun-facing side of the telescope, it's going to be about 185 degrees Fahrenheit. You could almost boil some water on that side of the telescope. But you've got these 5 layers of reflective material that actually attenuate the energy from the sun by 1,000,000 times, so that by the time you get to the other side of the sun shield, it's only, minus 388 degrees, a little bit colder than what we're used to here in Minnesota, but you could freeze nitrogen at this temperature. So it's pretty cold. But that's really important for the telescope to be able to function, because if you think about the near infrared, and if you've ever seen people use infrared goggles, or if you've been able to use infrared goggles yourself, that is, where you can see like people's bodies, their temperatures in the infrared. And so if we have our telescope or instruments at that temperature, it's going to emit its own radiation that the telescope's going to detect. So we have to make sure that it is much, much colder than that thermal radiation that the instruments are detecting, or emitting, so that it doesn't detect itself with the telescope. So here's another image with JWST back on Earth as it was about to undergo some testing in a gigantic vacuum. And you can see the people for scale, for how big the mirror is. So compared to the Hubble Space Telescope, JWST is about 21 feet, I believe, in diameter, and it's made up of 18 hexagonal mirrors. Each one of those is about 4 feet in diameter. So it's much, much bigger than the HST. So you can see why this is indeed a successor to the Hubble Space Telescope. Those mirrors are made out of beryllium, which is a super light metal, which is important if you want to send stuff into space. You want it to be as light as possible so that you don't have to use a bunch of fuel to launch it off of Earth. So the name of the game when you're developing a space telescope is how light can you make it be. So the mirrors are made of beryllium, but then they're coated with a very, very thin layer of gold because of its reflective properties. And so the amount of gold on the entire mirror, which is about 25 square meters in area, has the same mass as a golf ball. Or if you were to collect all of the gold off of the mirror, you would have a ball about the size of a marble. So if you can imagine how thinly that gold layer has been placed on the telescope, I just think that all of the processes that go into building this and the engineering is just incredible for this type of an instrument. And then on top of that, you have a very thin layer of glass, because gold is a relatively soft metal, and there's stuff up in space, dust and whatnot, and we want to be able to protect those reflective properties. So there is a thin layer of glass on top of it. So I mentioned that we're looking in the infrared. So why are we interested in clicked one too many times. Why are we interested in the infrared? Well, if you are here on Earth in the expanding universe that we live in, as space expands, objects are going to appear to be moving away from us, right? Because the space between us is expanding. As that happens, light that is emitted by a distant object is also going to expand. So the wavelength, you can imagine, is getting stretched to longer and longer wavelengths. And the infrared is a longer wavelength, or longer portion of the electromagnetic spectrum than the optical. And so if we're interested in looking far back in time to distant objects, we need to look at lower wavelengths, lower energy. And so here is another example that shows the electromagnetic spectrum. As that object is being, what we say, redshifted away from us, that light is moving towards redder, lower energy, longer wavelengths through the expansion of space that then, I pushed the wrong button there. There we go, that we want to be observing these objects in the infrared in order to, look at things in the early universe. Another reason why we're interested in the infrared is if we want to look at star formation, it turns out there's a lot of dust and gas in galaxies, which is important because gas is required to form stars. But if we look at it in the optical, the left image is a composite of 3 different wavelengths, so images that were taken at 3 different wavelengths in the optical portion of the spectrum. So we've got these 3 different wavelengths are detecting nitrogen, hydrogen, and oxygen. And so in the optical, because the gas and dust particles are so small and on the scale of the wavelength of the optical photons, that light gets scattered really easily by that material. But if we move to longer wavelengths, like the infrared, those photons aren't going to interact with that gas and dust in the same way that the optical photons do. And so on the right, we see the same part of the sky, the same Lagoon Nebula, but this is in the infrared. Both these images were taken with the HST, and we see all of a sudden there's a bunch of stars, right? We're able to look through that gas and dust if we're interested in star formation and star forming regions. And so using the infrared is a really important tool to study things like star formation as well. And so that's another reason why we would want a space telescope like JWST to observe in the infrared. So I mentioned before that JWST is located at the second Lagrangian point. And so here in the top, you can see the 5 different metastable gravitational locations associated with the Earth-Sun orbit. And so at these points, we say it's metastable because if you were to sit directly on that point and not be disturbed, you would orbit at that location relative to the sun and Earth as they are going through their orbits. So if you're at L4, you would always be at that location relative to the sun and the Earth as the Earth and the sun move in their orbital rotations. And so JWST is located at L2, where it turns out we've also put several other telescopes, like the Planck Space Telescope, Herschel. We've got some other telescopes out in that part of the sky. So it is located on the opposite side of the Earth from the sun, which means that when we have that Earth antenna that we communicate with and that sun shield, both of those are on the side of the Earth and the sun, and so they're never going to interact with the optics of the telescope, which is really nice because then we don't ever have to worry about daytime or nighttime observing because the telescope's always pointed away from the sun. This is located about 1.5 million kilometers from the Earth, and it took the JWST about a month to get to that location after it was launched in December 25th, 2021. And just another aspect of it being located there, unlike the Hubble Space Telescope, which is in a near-Earth orbit, once we send something out to L2, we can't fix it. So, there was this huge mission to correct the mirrors in Hubble, because when they first took images, it was out of focus. If that had been true for JWST, we would be done. Like, we wouldn't be able to get any observations because of its location. But luckily, everything seems to be working okay so far. So the JWST has 4 main instruments for taking its observations. So again, I've got the electromagnetic spectrum here just to orient you relative to the optical of where these observations are taking place. So there is the FGS, which is the fine guidance sensor, and it also has the near-infrared imager and slitless spectrograph. And so with this instrument, we're able to take really interesting images of exoplanets, and here, which we'll go into a little bit more detail in a little bit, is a spectrum of a transmission spectrum of an exoplanet, so looking at the atmosphere of the exoplanet. There is the mid-infrared instrument, which is great for, so this is going to be a little bit further away from the optical portion of the spectrum than the near-infrared. So longer wavelength, lower energy photons, and that is going to be great for taking images of galaxies and of things like Kuiper belt objects. So we're going to also be able to observe things within our own solar system with this telescope. It has a near-infrared camera, which is what that beautiful image of the Carina Nebula was taken with. And so that's going to help us look at star-forming regions, galaxy evolution, galaxy structure, and things like that. And then there is the near-infrared spectrograph. This is a whole new feat of engineering as well, that all of this new technology was developed specifically for this instrument. So what you're looking at is a set of little windows on this spectrograph. You can consider this thing as like a multi-object or IFU or integral field unit, if you've heard any of those terms before. But basically, each of those windows can be opened to allow light to go through, and then we can get a spectrum of an object or a spectrum of whatever light goes through it, that little window. Each one of those little windows is about the width of a hair. Okay, there are, I think it was about 62,000 of these little windows altogether, and you can take on the order of 100 to 150 spectra simultaneously. So using magnetic fields, they can determine which of the windows are open to look at different parts of the sky, and then they can get a simultaneous spectrum of things using this object. I just think it's mind-blowing to think about something the width of a hair, that they're these little windows that they're opening and closing to look at objects. So I should have probably explained this a little bit before, but when I say the word spectrum, what I want you to think about is we're going to think about very specific wavelengths and how much energy is coming from each of those wavelengths, okay? So this is really important if we want to understand the composition of an object. So it turns out each element on the periodic table has its own fingerprint in the spectra. So if you were to take a spectrum of hydrogen versus a spectrum of oxygen, it's going to look very different because of the different electronic transitions of the electrons within the atom emit at different wavelengths, and so you'll get energy at different wavelengths. And so we can use a spectrum of these objects to determine what it's made up of, what kind of processes are happening in these objects, and so that's a really important tool for really understanding things, because as astronomers, we can't just go into a lab and manipulate things like a physicist does or a chemist or a biologist, right? We just use light and images. That's our main tool. Yeah, so this near-infrared spectrograph is just a whole nother level of amazing, I think, in terms of collecting data. So why are we interested in using the JWST? So this is, I thought, was a nice representation of the types of objects that it's going to be looking at, or the types of science that's going to happen within the first year of the telescope's life. So you can see that most of the observations that are going to be taken have to do with galaxies and the IGM, or the intergalactic medium. So the gas and material that exists between galaxies in the universe. And then another large amount of time, I guess not huge, about 25%, 23% of the time, observing time, is going to be devoted to exoplanets and disks of protoplanetary disks of stars. So two very different scales of science and different realms of astronomy that are going to be done with this telescope. And then other things that will be done: stellar physics, supermassive black holes, a lot of interesting results will come up from that. Stellar population, so understanding how stars evolve and how the histories of galaxies, that's what we can do with stellar populations and the interstellar medium. A small amount of time will be devoted to the solar system and understanding things like Kuiper belt objects and comets, and then large-scale structure of the universe will also, we'll get some data on that as well. So now I'd like to go into a little bit more detail on these different aspects of science that will be explored with the JWST. So I mentioned protoplanetary disks and planet formation. So what I'm going to be showing from now on is actual data that has been taken with JWST. So this is all, fresh off the press within the last 12 months. Not even 12 months. I guess July 12th, I think, was the first download of data from JWST for science. So here we have a protoplanetary disk, and so with the JWST, we're going to be able to look at regions where planets are just starting to form. So this is an object called AU-MIC. It is a red dwarf star with a protoplanetary disk, and so these images were taken with the near-IR camera, which also has this thing called a chronograph on it, which allows the observer to cover up really, really bright objects in the sky, and so they're able to see dimmer things around those. So if where you see the little, cartoon star is where that red dwarf star would be located, but if that chronograph weren't there, we would just see the star. It would be saturating the image. We would not be able to detect the disk. But because this near infrared camera has this chronograph capabilities, we're able to look at things like the disks and very diffuse, dim things that are near bright objects. So this protoplanetary disk is located 32 light years away. So there's probably other things that have happened within the past 32 years that might have changed this if we were to, able to just go there instantaneously and see what's happening. But the scale of this object, for reference, that dashed circle is about 5 AU from the star, so on either side. So an AU is the average distance between the Earth and the Sun, and so 5 AU is about where Jupiter is located. So what we're able to observe here is the protoplanetary disk as close as Jupiter's orbit to the star, and it extends out to a full diameter of about 60 AU. So that's about the size that we have here. So it's about 60 times the distance between the Earth and the Sun. In the top, we have a shorter wavelength infrared observation, and in the bottom we have a longer infrared observation. And you can see that the top is brighter. And when we have brighter emission at these shorter wavelengths, that tells us a little bit of information about the size of the gas and the dust that we're observing. So from this, we can learn that there's probably a greater proportion of smaller little dust grain particles than larger ones that would be emitting at that longer wavelength in that bottom image. This is a blown up version of that spectrum that I was showing before. So this is, as I mentioned before, a transmission spectrum of the atmosphere of an exoplanet. So with the JWST, we're going to be able to do much better studies of exoplanets and what they're composed of and what kind of atmospheres they have. And so this is WASP 96b. It is a hot gas giant, which means it's going to be something like Jupiter or Saturn, but it's hot, which means that it's close to its star, okay? So it's going to be orbiting closer to its star than either Jupiter or Saturn do here in our solar system. It's located 1,150 light years away, so we're starting to look further back in time now as we go through these objects. And it's using the near-infrared imager and the slitless spectrograph. So this is a spectrum, so this is coming from the slitless spectrograph. And what we see in this spectrum is a lot of water emission. This isn't a new detection. We knew that this object had water in its atmosphere, but we're able to get much more detailed information. And so there's a best fit model. That's what that blue line is, running through all of those little white data points, so that we can start to understand the cloud composition, how dense are those water molecules, and hopefully we'll be able to detect some other elements as well in other systems, I should say. Then moving back to the Carina Nebula, I wanted to point out some of the interesting physics that's happening here. So again, this object is about 7,600 light years away. It's using the near-infrared camera. And if we look closely at the different shapes and structure in this object, we can see these pillars. So what we're unable to see in this star-forming region is above this image, there are these really hot, young, massive O and B stars that are emitting a ton of radiation that is ionizing the gas, and it's blowing, is emitting so much radiation that it's pushing this material away. But there are regions where you've got these higher density structures, and you've got like pillars that will stand up against this force of radiation from those massive stars. But within that, the reddish orange material, that's where gas is continuing to collapse to form new stars. And so you have areas where the gas is actually blowing out because there's a new star in that area that's starting to emit a bunch of radiation, and it's going to be pushing material out. So there's regions where there are blowouts happening from new young stars. The little wispy blue strands or streams that you see coming off of that cliff area, that's actually hot gas and dust that's been ionized by that really hot, high-energy radiation from those massive stars out of the frame of the image. So you're seeing these hot gas and dust ionized particles that are moving away, sort of lifting off of that material. So there's a lot of really interesting things, in addition to just this being a fascinating thing, but there are a lot of interesting physics and new discoveries that will be made with these observations. Moving on with stellar evolution, the previous one was looking at the birthplace of stars. We're also going to be able to study the death and the evolution of these stars. And so here we have the Southern Ring Nebula. In the left, we've got an image with the near-infrared camera, and on the left with the mid-infrared. And so immediately you can see that there's different resolution between those two images. So given the size of your telescope and the wavelength that you're observing, that's going to determine the resolution that you get in your images. And so at longer wavelengths, we're not going to get the same resolution or the same fine details that we can get using the shorter wavelengths, like in the near infrared. But we're still able to see vastly different things between these two parts of the spectrum. So in the near infrared, the light from the stars is really dominating what we observe. So light from those stars is reflecting off of the light. That's what that blue sort of reflection is happening in the center. And where you see that star spoke type object in the very middle, that's not actually the star that is in its final stages of life. There's actually if you look on the right, that little reddish dot just to the left and below that white dot, that is a white dwarf. And so that's a star that was about the mass of the sun, a little bit more massive than the sun, that reached its end stages of life. It could no longer undergo nucleosynthesis, putting hydrogen and helium together to form heavier and heavier elements to emit energy to combat the force of gravity. So gravity collapsed in on it, and it went through these stages where it was expelling its outer atmospheres of the star until it was just left with this white dwarf in the middle. And so those rings and those sort of bowl structures that you see are the atmosphere that was blown off from that the star before it became a white dwarf. And so when we look in the mid-infrared, we're able to see that white dwarf in better detail and get a little bit more information about the dust and the larger particles, dust grain particles in that object compared to in the near-infrared. And if we go to even larger scales and move beyond our own galaxy, we can see really interesting things like this galaxy group. This is called Stephan's Quintet. It's actually a galaxy group comprised of only 4 interacting galaxies, but there's a 5th one in there that the one on the furthest to the left just is much closer to us, but it just appears to be interacting with this larger system. But the interacting galaxies, the group galaxies, are located about 290 million light years away. So now we're really starting to look back in time, right? We're not just thinking about a few light years or thousands of light years. Now we're in the millions, hundreds of millions of light years. So that light has been traveling for a long time to get to us. This image is taken with the near-infrared camera and the mid-infrared camera, and something that I think is phenomenal about this image is that over 1,000 images were taken with these different instruments and combined together to create this image. Okay, so there are over 150 million pixels that have been mosaicked together because they had to look at different parts of the sky, they had to look at different parts of the electromagnetic spectrum in order to put this image together. But from this image, we're going to be able to study a supermassive black hole or I should say, the collection of these images. We'll be able to study a supermassive black hole that is actively accreting material and blowing out jets in one of the objects as it is going through this interaction where these galaxies are merging together. So that is a little tease on the galaxy evolution. And then this is an initial deep image taken by the JWST looking at a galaxy cluster. Now this galaxy cluster is located 4.24 billion light years away. So we think the universe is about 13.8 billion years old. And so now we're looking at the universe as it was, 3/4 of its age. Okay, so all of the light that we're collecting from this object, at least associated with the galaxy cluster, is 4.24 billion light years. And so something that I think is pretty amazing is here is a zoom in on a couple of the galaxies associated with this galaxy cluster. And in the top row, you see images that were taken with the Hubble Space Telescope. And in the bottom, you're seeing images with the JWST. And so the detail that we're able to get in these objects with the JWST is just phenomenal. You know, everything that we got from HST, we're just like, whoa, this is amazing, this is great. This is next level with JWST. And so we'll be able to study in greater detail objects that are further away here. And then if we push ourselves back even further in time with the JWST, and we look at galaxies, distant galaxies, that's what that's supposed to be, distant galaxies behind that galaxy cluster, we're able to identify objects that are located 11.3 to 13.1 billion light years away, all right? So 13.1 billion light years compared to the universe that's 13.8 billion light years. We are starting to look at some of the first galaxies in the universe, and this is really, really exciting. And we're identifying them, you know, more easily with the JWST than we've been able to do previously. So what you're seeing here is a combination of the near-infrared camera, which took that deep field image, and then spectra from that near-infrared spectrograph. So using those little hair width windows, they opened 48 of those simultaneously and got spectra of objects in the cluster and around the cluster. And so on the right, then you're seeing 4 of those objects located at different distances away. So at the top, that's something that's closest to us at 11.3 billion light years, and at the bottom is a spectrum of an object that's located 13.1 billion light years. And so remember how I was talking about elements having these fingerprints, and so what the astronomers use to identify where all of these objects are located in space or in distance away from us is hydrogen and oxygen emission lines. So oxygen and hydrogen from these objects is detected, and we can see how it's been redshifted, how have those wavelengths been lengthened as the universe expands, and that is how we can tell how far away these objects are from us. So I wanted to leave plenty of time for questions for the audience and for those viewing online, so I'll just wrap up with saying that there is so much more that I didn't get to go into detail here that the JWST is going to do. Protostars, I kind of hinted at that with the Carina Nebula. Black hole physics, like I said, when we're getting all of those different images of interacting galaxies that will be triggering supermassive black hole accretion, we're going to be able to understand black hole physics with those observations or learn more about it. We're going to observe the youngest galaxies we've ever detected. Didn't even go into Kuiper Belt objects or comets, but we'll be able to do solar system objects. And then when we look at the distances between objects and galaxies, we'll be able to start to make more measurements or new measurements of large-scale structure in the universe. And that's just some of the things that I didn't get to touch on. So yeah, I will pause here, and I'm happy to take whatever questions that you have. So yeah. Right, we'll go to Natasha, raised her hand right away.
I'll start with the first question. I only have a minor in astronomy, but I love space. I work for a human space travel company. And I always wonder, what is your favorite celestial object?
Oh, my favorite celestial object. I mean, I'm probably biased right now because of my 17-month-old loves to find the moon whenever we go outside. And so now I'm just like learning everything I can about the moon to obviously she's not understanding what I'm telling her, everything I'm telling her now, but like it's just a constant and always really gorgeous. So the moon is probably, I'm biased towards that. Also probably biased towards I can jump to back here, the galaxy that I showed at the very beginning. This has a clever name of NGC 6946, or it's also sometimes known as the fireworks galaxy. And I've spent a lot of time trying to understand the magnetic fields there. So I probably have a little bit of a love-hate relationship with that object, so to work through that data, but it also has a big place in my heart. So yeah.
Yes. Now that the Arecibo telescope has been destroyed, are they going to replace it? What are they going to do?
There's still a lot of discussion about that. I don't know if you've heard of China's FAST telescope, but it's sort of like the next size up from Arecibo. But we would love to have our own large single dish telescope that we would be able to use. Unfortunately, I'm not able to say definitively what that next instrument will be that the U.S. has a hand in, but there's definitely still discussions about, what do we want that to look like?
That is
and
so
what can that
sad.
be. I know, it was.
It breaks our heart.
When I found out there was a video, it took me a couple days to be able to watch that because I was like, I don't think I can see that. Like
No.
I climbed up. I've been in at one point I got to visit the telescope and I got to climb up the scaffolding to see everything, and it was an amazing instrument, and yeah, it was
Thank you very
devastating.
much.
Yeah. Yeah.
Hello.
Hello.
I have a kind of naive yet oddly technical question. I'm familiar with Lagrangian points from science fiction and stuff, and I got a kind of a nebulous, no pun intended, I'm sorry, a nebulous idea of what that is. Is it like a large area where you can park things that will stay in that spot, or is it like you mentioned that there were several objects in that spot, and I'm just kind of, I'm not sure how that works.
Yeah, great question. Because I did not, happy to talk more about this, but I obviously didn't want to spend too much time on it because I want to go into, be sure to show you some pretty space pictures. So one way to think about the Lagrangian points is, the actual center of mass for a system of objects orbiting each other is in a different location. That would be a stable spot. Like if you were to stay there, you're going to get into that center of mass. You would stay in that spot relative to the motion of the other objects. So these are, it's like a black hole is an infinitesimally small spot, right? This is going to be a very precise spot. But the way that we get around that, as I said, that these are metastable locations, or metastable, gravitationally metastable, is what I want to say there. So if you think about like a stable gravitational point would be like a valley, right? If you move a little bit, you're gonna go back down the hill and you're gonna end back in the valley. An unstable would be a hill, right? If you're on top of the hill and you move a little bit, you're gonna roll down that hill. A metastable is like a saddle. So if you go in one direction, you're gonna be lucky, if you're lucky enough to go in the right direction, you're gonna be forced back in towards that hill area, or the valley area. If you go in the other direction, it would be like a hill, and you're gonna roll away from it. So the way that they get around that is they have the satellites orbit around these points. So the JWST is actually just gonna be a hair closer to the Earth than the L2, so that it's gonna constantly want to go towards the Earth and away from L2, but because the propulsion system is on that side of the sun shield, it can push itself back. Meanwhile, it's going to be orbiting around that point in order to maintain more of a stable position relative to L2. So that means that if we think about putting these things at different orbits around L2, we can put multiple objects there, right? Because they can be at different orbits. So that's why there are a variety of space telescopes that can be at the same Lagrangian point. Yeah, and another thing about JWST, I think it's at one of the larger orbits around the L2, and the larger your orbit, the less energy it's gonna take to stay in that orbit. So they're gonna be able to use less fuel and propulsion to keep it there, but I think it's still every 21 days that they have to correct its position, because if you think about that, solar radiation is constantly trying to move it, the gravitational tug is constantly trying to move it, and then when you turn the telescope, right? That's going to change how it's interacting with all of those different forces on it, and so that's also going to affect how it orbits, and it will need corrections for that as well.
Thank you.
Mm-hmm.
I'm sure you know that the numbers don't add up. A lot of people talk about the dark matter, the invisible third of the universe we just can't see.
Yep.
I've always kind of liked the idea of modified Newtonian dynamics, but every time we put it to the test, it fails miserably.
Right.
Do you have any thoughts on this missing chunk out there?
Yeah. I'll admit this is not my wheelhouse of research, so I don't have too much experience firsthand with this. But I think that if you think about particle physics as well, and the standard model that we use to explain all of the atoms and subatomic particles that we understand making up everything in the universe, that also has a lot of issues. Well, not a lot of issues, but it also breaks down in a variety of places. And so I definitely feel like maybe I've been indoctrined as an astronomer with all of the classes and the different talks that I've been to feel more strongly inclined towards the particle model for dark matter rather than modified Newtonian physics. But I mean, right, how long did we have Newtonian physics before Einstein came around? A couple hundred years before Einstein came around and, did general relativity to like launch us into the next understanding of gravitational interactions and how space and time are connected. So if I had to put my money down on a bet, I would go with the particle model, but you never know. Yeah.
You speak about gravity. It's only in my lifetime that we've actually done research on gravity. Is there anything new coming along in that field?
I think that with the detection of gravitational waves and those instruments that we are now actually able to verify another one of the predictions of general relativity, by observing how space-time is affected by the merger of massive objects. I think that is, it's opening a whole new world of understanding gravity and gravitational interactions and extreme physics, right? Where if you think about the physics of a massive object, it's nothing that we can fathom through our normal interactions with gravity here on Earth. And so I think that those new observations and the future of gravitational wave studies is going to be really interesting in terms of our understanding of gravity in extreme situations. So, yeah.
So you said that they have marble's worth of gold that ends up getting or the entire size of like a tennis court. How does that flattening happen? How do they manage to spread it so thin?
Yeah, so there's a process called vacuum deposition. So basically they would take these little, 1.2 meter, 4 feet hexagonal mirrors, put them in a huge vacuum chamber, and basically evaporate gold and have it deposit onto the mirror. It's a really interesting process and phenomenal that we're able to get that sort of precision in a very thin layer of anything on an object. So, yeah.
Do I get two questions?
Sure. There's no one behind you yet.
This might be more in your wheelhouse. So when we're looking out at farthest distance galaxies, we're seeing new galaxies but old light.
Right.
So from galaxy structure standpoints, similar to when we watch our children grow, what are some of the things that you see in new galaxies, and how do they develop into older galaxies, and what are some of the norms in that? And then my second question is, what are the limitations of James Webb? Does it have a blind spot? Are there certain things that it just can't do that we'd really like it to do, or?
Yeah.
Yeah.
Great, thank you. So to your first question, thinking about galaxy evolution, so when we're looking back in time, we also can think about the fact that the universe was much smaller, right? Everything was much denser, everything was much hotter. So when you're forming those initial galaxies, they're more likely to interact. So if you're forming some dwarf galaxies or even some massive galaxies, you're gonna have a lot more collisions, a lot more mergers, a lot more interactions between those systems earlier in the universe. Another thing that James Webb is going to help us understand, and there are some hints towards this, though, a lot of people are trying to get the results out really fast, and the peer review process is still a way to make sure that things aren't going out too fast, but that the way that stars form might be different in that environment than the environment that they form in today. So if you think about the composition of the universe earlier on, is mostly hydrogen. I mean, the universe is still mostly hydrogen, but there was a lot more hydrogen, helium and lithium, a little bit of beryllium, but not heavy elements like carbon or oxygen or iron or anything that we depend on to be living, breathing human beings here on Earth and on our planet. And so without those heavier elements, how gas can collapse changes. Because it turns out if you have heavier elements with those different electronic transitions than you have in a hydrogen atom, heat and radiation can escape differently from the interstellar medium, which allows gas to cool more efficiently and collapse to form stars more efficiently today than we think could have happened back then. So in addition to galaxies probably being smaller, clumpier, interacting more, having a lot more interesting interactions between galaxies, the way that stars were forming is probably different. And there's some hints at that in some of the initial JWST observations, that maybe what we call the initial mass function, or the number of stars per mass bin in a given star formation event, might be different earlier on in the universe. But there's a lot more data that needs to come in to sort of verify that, or contradict what we know today. So that was question number 1. Question number 2, I really got excited about question number 1. I've already forgotten question number 2. Blind spots of JWST, right. So yeah, what can't JWST do? Well, JWST can't do anything outside of the near infrared. So if we think about this electromagnetic spectrum, all of my research relies on radio telescopes, right? I can't study magnetic fields with the JWST. I can learn things about dust grain and possibly dust alignment. There is some polarization studies that can be done in the infrared portion of the spectrum, but as far as I know, there's no polarization polarimeter on JWST. I say that and I'm gonna immediately get off stage and double check that. I don't want to dig myself a grave there. So from my standpoint, it's blind to magnetic fields and that part of astrophysical objects. Another thing that there's talk in the astronomy community is that we don't have a next generation X-ray telescope in the works right now. And so there's a lot of interesting high energy physics, right? X-rays are higher energy, and gamma rays are higher energy than the optical or infrared. And so those study extreme environments as well, like black holes. And so being able to understand and observe those types of things won't be possible with the same types of things like X-ray binaries or things like that. We won't get the same information if we look at them with JWST. So that's sort of just a basic, answer.
Excellent, thank you.
Yeah.
It just puts in perspective it's just a fascinating tool, right?
Yeah.
But scope and range is something that we don't always get that information from the public. But
Right.
now going back to the prior question with the age and the composition of the elements and things that are around in the galaxies, with the magnetic structure, are there buckets that you're seeing that the magnetic signatures of aged galaxies tend to fall into? Are there patterns that you're seeing and going, oh, this is a unique structure that's related to this specific either age or structure within that aged galaxy?
Yeah.
That you can kind of predict and fall into sort of a bucket?
Yes.
Does that make sense?
Yeah, no, that's a really, really interesting question. So we have a hard time studying magnetic fields too far away from us. So we use this thing called Faraday rotation measure. So if you've got a magnetic field in an ionized medium, which most of the universe is, and you have light travel through it, the orientation of the photon, the polarization of the photon is going to be affected by that. And so you can use that to measure the presence of magnetic fields, the strength of magnetic fields, and the orientation, if you know something about the gas. And so locally, we see spiral galaxies like the Milky Way seem to have spiral magnetic arms. So we see that these large structures of the beautiful spiral galaxies that you'll see images of, they tend to have these large structures of magnetic fields. But observing those in distant objects is hard because of the emission that we get from those objects is relatively weak compared to the optical or infrared emission that we're getting. So we are starting to have more data to sort of play around with how those magnetic fields evolve with time with things like the Square Kilometre Array, which is a gigantic radio telescope spread out between Australia and South Africa. And so there's a lot more data coming online to start to think about how those magnetic fields change with time, but we still don't really understand the dynamo process that creates those large-scale magnetic fields. So observers are trying to collect information, tell it to the theorists. Well, the theorists are creating their models, and then we're going back and forth trying to figure out how we can explain those things. So in terms of the evolution of magnetic fields, the idea of these, the strength of the magnetic fields early on in the universe is also going to be, we might be able to get some information about that with JWST in terms of that initial mass function and whether or not the magnetic fields might be playing a role there through that. Yeah, Natasha.
I really have enjoyed this panel, and thank you so much for coming and talking. I would love to keep talking for a few more hours, but we are out of time. Any last comments you have for us?
I'm happy to stick around if anyone wants to chat a little bit more. I should have thrown my email address up here, but if you go to McAllister, you can find me there, and I'd be happy to answer questions via email as well.
Ooh, give it up for
Can I
Anna
ask
Williams.
just one question?
One more question.
Something that, I don't know if it's quick or not. For decades, I've been working with young children, teaching them about astronomy, showing them telescopes and so on. And I have very rarely succeeded at getting any of the kids to keep their interest in astronomy past age 13. And only our brain structure literally comes from the fact of tens of thousands of years of looking at the sky. That's why we like patterns, is because the sky is so important to us. But I'd like you to mention like your first telescope and whether or not you read Mickey Mouse Goes to the Moon when you were little, or how you got interested and how you managed to stay with it to where you are now.
So there was a Time magazine article about the expansion of the universe. I think it probably came out in '98 or something like that. I think I was in 7th grade, or maybe it was closer to 2000, 8th grade, that I just was like, what? The universe is expanding. How old is this? Like, when is the universe going to die? Like this idea, like the universe dying too. That all fascinated me, and I've always loved math and physics. So I think that was probably the thing that kept me going back. I mean, I diverged. I thought I was going to be a veterinarian. I thought I was going to be an OBGYN. Then I thought I was going to be a veterinarian. And then I did my honors thesis in astronomy in undergrad, and I loved writing that. And I was like, well, if I like writing this and creating new knowledge in astronomy, I'm going to stick with it. But I guess for me, it was this Time magazine article about the expansion of the universe and the end of the universe that kind of made me really excited to continue pursuing physics and math. Oh, yeah? Yeah. Great. Well, thank you. Thank you all very much.
Thank you, Anna Williams.